I'm going to introduce the last speaker of the day. So it's a pleasure to introduce Mariana Rosas Ribeiro. Actually, she's Brazilian, but she's doing PhD with Maria Brasa Moroz at the University of Rovira e Virgili. And she's going to talk about on infinite chains of numerical semigroups.
Thank you, Luciane. I'm going to talk about some results in that first year about infinity chains and numerical semigroups 3. So many authors have been looking for the number of numerical semigroups with fixed genus G, especially after Maria Brasa Moroz conjectured that sequence has a Fibonacci-like growth, plot twist, numerical semigroup. One of the tools to attack that problem is organize all numerical semigroups in a tree, which every level and that tree have all numerical semigroups with the genus G. Level G, numerical semigroups with the genus G. And here we have an example that tree is structured up to genus 6. And in that tree, we can see some chains which will be continuing and never ends. That is our infinity chains. And it's interesting that computations show us that infinity chains are very rare in that tree, but they keeps our tree alive. So let's study that infinity chains. Okay, here in red we have infinite chains. Some preliminaries, numerical semigroup is a subset of naturals, positive with 0. 0 is there, it's additively closed, and its complement is finite. Okay, we can enumerate that elements. So 0 is using a lambda enumeration. 0 is lambda 0, and the next one is lambda 1, and so on. And the genus of numerical semigroups is the cardinality of the complement. Multiplicity is the small element non-zero. Conductor is the element, the small element from which all naturals are in the numerical semigroups greater than conductor. Okay, and the left elements are the elements in numerical semigroups is smaller than conductor. And we also have minimal generators, and minimal generators greater than conductor are very important to construct the tree. They are called effective generators. Some special cases is the ordinary one, which has interval as a complement, and hyperelliptic semigroups. So here I want to highlight that infinity chain is formed by hyperelliptic semigroups, and that is the ordinary ones. So that tree works very well. Okay. In 2012, Alexei proved the behavior like Fibonacci holds at infinity. But we don't know still if the sequence is increasing. So let's now understand how the tree is constructed. We start by naturals and take out every effective generators at a time. Okay, for example, here one is a generator, so I take out E and I get that sum group. And here I have 2 and 3 as effective generators, and I have 2 numerical semigroups. And for instance, here I have 3, 7, and 8 as generators, minimal generators, but only 7 and 8 are effective. So we get 2 numerical semigroups. And another thing is if I take a numerical semigroup, I put the conductor -1, which is the Frobenius number, I come back in the tree. Okay. And in the tree perspective, we can change some names. I can refer to numerical semigroups as nodes, and I have children of a node, and for every child I have a parent, and for a node I have descendants. For instance, here in red, its node is a descendant of this blue node here. And we also have leaves, nodes with no child, stick, nodes with only one child, and bush otherwise. Okay. That lemma gives us what are the child of a numerical semigroups, grandson. So infinity chance now. In that paper, Brasamaros and Bullingen characterized when a numerical semigroup belongs to an infinite chance. And they did it just using the left elements. So numerical semigroups is in an infinite chance only if the GCD of left elements is different from 1. Here again, we can see the 3 up to genus 9. So we proved that if a numerical semigroup is in an infinity chain, so it can be at most 2 children in an infinite chain, and that children are B, or the numerical semigroups without the conductor or without the conductor plus 1. And we also proved that if a numerical semigroup in an infinity chain have a few children, necessarily it has a child with no infinity chain, because we have this proposition. Okay. For that, we did this definition of fertile numerical semigroup when most of its children are in infinite chain. So a fertile is like this one, or this one. That is all options. So by proposition, a numerical semigroup fertile has only one child if it is hyperelliptic or the naturals. And it is type 2 if it's equal the naturals without 1. And about the third case, we can, that proposition. The third case just happened one time at every 3 genomes. We have its phase. And with that, we can prove this theorem, or say the number of numerical semigroups in an infinity chain with genomes fixed genomes G is at most unhealthy the NG. Okay. We have found another properties in the tree format by only numerical semigroups in an infinity chain. And the property is a self-replication. And we have that definition. It's very important for self-replication. We define a push of the numerical semigroup by its multiplicity, as I'm just plus the multiplicity in all elements, and I unit 0. Okay, with that push, it's interesting. I hope explore more because it has another properties, but for now, we have this one. For sub-tree of the tree of numerical semigroups in an infinite chain, the sub-tree with only multiplicity 4 begins this way. And we have this structure will be replicate along the tree, and it happens by push. So, for instance, here we start this way, and F is equal to the push of A by 4, its multiplicity, and here. The push of F by 4 is equal to 2 times the push of A by 4. And here, the structure to 40. And that way we can account the number of numerical semigroups in an infinite chain with genomes G and multiplicity 4. And we also have found that behavior on multiplicity 6 begins this way, And with that theorem, we prove Tn, Un, Vn, no, Tn, Un, and Xn will be continuing as a line, okay? And the Sn and Vn belongs to any infinity chance. And we have found where that descendants, infinity descendants of Sn, Vn have two children, two infinity children. So here up to 16, we have two replications, and SE1 and V1 belongs to just one infinite chance. But here we can see 5 self-replications. In the highlighted, we have S3, V3, and the 3 infinity chance which S3 belongs to, and the same for V3. So this way we can account the number of numerical semigroups in an infinity chance with multiplicity 6. And that's it. So, thank you very much.